Okay, greetings. So welcome to today's class. So just a quick recap of what we did yesterday. So in yesterday's class we were discussing, we started with the discussion on internal combustion engines. We looked at various classes of internal combustion engines based on different attributes, and we essentially discussed that in this particular course we would look at reciprocating internal combustion engines, both 4-stroke and 2-stroke, and petrol and diesel engines. And after doing that, we started looking at the components of an internal combustion engine. In a typical IC engine, there are 3 blocks: the cylinder block, the cylinder head, which is on top of the cylinder block, and the crankcase, which is at the bottom. Okay. So we started with the cylinder block. We essentially learned about its construction, some features of cylinder blocks. Then we looked at cylinder inserts or cylinder sleeves. That is where we stopped in the previous class. So let's build on from there, and then let's look at more components today. Okay. So the next important component in the which is fit within the cylinder block is the piston. So the piston is a component, on which the the forces that are generated due to the combustion process act, and the energy, thermal energy, is converted to kinetic energy. Okay, so that way it's a very important component in an internal combustion engine. And if you look at a typical piston, okay, the construction is something like this. So if you look at the exploded view first, you have the piston itself, and that is fit in the cylinder or the combustion chamber using what are called as compression rings. Okay. So we have a very tight fit between the piston and the cylinder. The reason is obvious, right? Because during combustion, the pressures in the cylinder are going to be very high, and even if we have a small opening somewhere, right, between the piston and the cylinder, the hot gases are going to escape and we are going to lose energy, right. So we want the gases that are generated due to the combustion process to act on the piston and push it down. So we don't want any leakage between the piston and the walls of the cylinder. So compression rings essentially provides us with a tight fit between the piston and the cylinder wall, okay, to prevent any potential leakages. Then we have what are called as oil rings. Of course, you can you will observe when you watch an engine that this piston is going to move up and down at very high speeds. Like typical engines operate wherein the crankshaft, which is rotated by this piston, rotates at a few thousands of RPM. So we are going to have like maybe one stroke of the piston, right, in the order of, in a time interval in the order of tens of milliseconds. So that's going to be very fast, right. So in other words, in a matter of 1 second, we may have like the piston undergoing, let's say, strokes in the order of 10 power 2 or 100 strokes. So that's essentially a lot of strokes, right, in a very small interval of time. And we essentially need to ensure that we lubricate the surface of contact between the piston and the cylinder, such that we reduce the frictional effects which oppose the motion, that will reduce the energy loss due to friction. And not only that, like it will enable smooth motion of the piston on the cylinder walls. Okay. An oil ring essentially helps us to wipe the engine oil or the lubricating oil on the inner surface of the cylinder, and that helps in the lubrication. Okay. So that's the function of an oil ring. Then we have what is called as a connecting rod, which then connects the piston to the crankshaft. Okay, we will come to the crankshaft shortly. Connecting rod, as the name indicates, connects the piston to the crankshaft. So, the connecting rod is fitted to the piston body through what is called as a gudgeon pin. Okay. So, this is a pin which holds the connecting rod, which connects the connecting rod to the piston. Okay. So, you insert the connecting rod and then you align the holes on the piston body and the connecting rod, which you can see, and then this pin is just fit inside, right, and held by clips. So, that is how the connecting rod is fixed to the piston. The other end of the connecting rod has these what to say bearing shells, like which will go and rest on the so called journals, like of the crank pins on the crankshaft. We will come shortly to the crankshaft. Okay. So, this cavity you can see will go and sit here, for example, okay, on the journals. You just fit it, that is it, right. So, this is like a simple mechanism, right. So, what we learn as a slider crank mechanism in basic kinematics, right. The piston essentially forms the slider, okay. So, that the translational motion of the piston is converted to a rotation of the crankshaft, okay, through the connecting rod. Okay. This connecting rod is mounted on these journals, okay, what are called as crank pin journals. This is what is called as a crank pin. Okay. So, this is the crankshaft. The piston essentially is connected to the crankshaft, and this end of the connecting rod rests on the crank pin. Okay. It is mounted through some bearings. Okay. So, you can see a very simple 2D diagram. So, this is the axis of rotation of the crankshaft, let us say the central axis. So, you can see these pink colored elements, right, those are the crank pins. Okay. So, each piston goes and sits on this crank pin. So, if you have a multi-cylinder engine, in this case there are 4 cylinders. So, consequently there will be 4 pistons and 4 crank pins. So, each of the pistons will be fitted to each one of these crank pins, and as the pistons move up and down, they are going to rotate this crankshaft through the respective connecting rods. Okay. So, that is what is going to happen. So, this is what is called as a crank pin, and what to say other end of the connecting rod sits on a bearing on this crank pin journal. Okay. And you can immediately see that there is a distance between the axis of the crank pin and the central axis of the crankshaft. Okay. That is what is called as the offset of the crankshaft. So, this component is a crankshaft, what we are now discussing, and there is something called as a crankshaft offset. So, what is the crankshaft offset? It is the distance between the axis of this crank pin and the central axis of the crankshaft. Okay. And twice the crankshaft offset is going to be equal to the distance travelled by the piston in one stroke. Okay. So, obviously like if my piston is at what is called as a top dead center, we will define what is called as a top dead center and a bottom dead center shortly, and let us say the piston is the top of the cylinder, it moves to the bottom of the cylinder. During that motion, this crank pin is going to rotate by 180 degrees. So, the stroke of the piston is going to be equal to 2 times the crankshaft offset. Okay. So, that is the definition of this crankshaft offset. Okay. And we can see all these counterweights or what are called as balancing weights, which are essentially attached to the basically included in the crankshaft, just opposite to that of the crank pin. So, if you see the crank pin here, you can see these balancing weights at the other end. Why is that? Like because the connecting rod will apply a force on the crank pin that will have two components. One will be a tangential component which will rotate the crankshaft, and there will be a radial component which can cause vibrations. Okay. So, what we do is that like we attach these counterweights or balancing weights to reduce those vibrations to the maximum possible extent. Okay. So, that is what we do. And additionally, the crankshaft is also mounted on bearings. So, you can see what is called as a main bearing journal. So, the crankshaft is also mounted on bearings to support the crankshaft, because crankshaft is going to rotate at thousands of RPM, and you can imagine in a multi-cylinder engine there are going to be different connecting rods that are going to apply forces on the crankshaft, right. So, it should be well supported, and this entire crankshaft is placed in the crankcase, okay, and the crankcase acts as a sump for engine oil. Okay. So, by and large this crankshaft is going to be immersed in that sump of oil. So, it is going to be well lubricated. Okay. As a result, we have what is called as an oil slinger. So, what happens, like imagine the crankshaft rotating at thousands of RPM, what is going to happen? It is going to create, it is going to churn the oil, right, and the oil may just splash around. So, when we come out of the crankcase, like this end of the crankshaft is going to be attached to what is called as a flywheel, okay, which will be then connected to the clutch. Okay. We will look at the flywheel more carefully when we come to the clutch, right. So, that is going to be connected to the flywheel, and so when this entire assembly is placed in the crankcase, there are seals at both ends to ensure that the engine oil does not leak, right, from the crankcase. But when this crankshaft rotates at high speeds and the engine oil is going to be splashed around, there is a chance that the seal may get damaged and the oil may start to leak. In order to prevent that, we have what is called as an oil slinger, which will reflect those waves, the engine oil waves which are generated due to the fast rotation of the crankshaft. Okay. So, that is a surface which will basically ensure that the waves do not cause significant damage to the oil seals in the crankcase. Okay. So, that is the function of an oil slinger, and of course, you can see these oil holes through which engine oil flows, so that like crankshaft is also well lubricated. Okay. And there is something called as a timing gear, which we will see shortly, because in a 4-stroke engine, in the cylinder head there is something called as a camshaft which will operate the inlet and outlet valves, okay, and that is operated by the crankshaft through what are called timing gears or timing belts. Okay. We will look at the significance of the timing gear shortly when we come to the valve assembly and its actuation. Fine. So, these are the different components of the crankshaft. So, we have looked at the cylinder block, the crankcase. Now, let us go to the cylinder head. Okay. So, that is the other that is the third chunk or block as far as the 4-stroke engine is concerned, right. So, what happens in the cylinder head? This is a bottom view of the cylinder head. So, imagine that you flip the cylinder head, place it on top of the cylinder block and then bolt it, okay, using a gasket in between to prevent leakages, right. So, we are looking at the bottom view of the cylinder head. You can immediately see that there are, of course, this is a 4-cylinder engine once again. So, you can see the numbers 1, 2, 3, 4 refer to the corresponding cylinder number, and you can see that there are what are called as intake or inlet valves. Okay. These are also called inlet or intake valves, and there is what is called as an exhaust valve for each cylinder, and like there are paths for circulating the engine coolant, or water for cooling the cylinder head also, because all engine components are going to get hot. So, we need to cool them, right. So, the coolant or the water is pumped through even the cylinder head to keep its temperature under operational limits, and you can see that there are holes through which you bolt the cylinder head to the cylinder block, right. You keep a gasket in between and bolt them together. Okay. So, what is the function of this intake valve? Intake valve or the inlet valve is used to take air or fuel air mixture depending on the type of the engine. We will discuss these aspects shortly when we go to what is called as mixture preparation and charging of engines and so on. So, used to take air or fuel air mixture into the cylinder / combustion chamber. Okay. So, we will use the words cylinder and combustion chamber interchangeably in our discussions in the scope of combustion. Okay. So, that is what. So, that is the function of an intake valve. Okay. Similarly, as the name what to say indicates, the exhaust valve is used to remove the exhaust gases. What are the exhaust gases? They are the products of combustion, right, because as we discussed, combustion is a process by which the hydrocarbons in the fuel are oxidized into H2O and CO2 if the combustion is ideal. But then like we are never going to have like ideal oxidation, there will be like other byproducts also like carbon monoxide, unburnt carbon, right, and other what to say gases also, like which we will look at when we look at emissions, right. So, the exhaust gases which are the byproducts of combustion, right, from the cylinder. Okay. So, that is the function of an exhaust valve. So, the intake valve and the exhaust valves along with their actuation mechanisms are assembled in the cylinder head. Okay. So, that is a very important set of components because they need to be controlled very accurately for the proper operation of the cylinder. Okay. So, typically let us say like to just give you a rough idea like of how fast these components operate. Let us say like we consider a simple example where let us say the crankshaft is rotating at 3000 revolutions per minute. Okay. So, 3000 revolutions per minute is going to be what? How many revolutions per second? 50 revolutions per second, right, I divide by 60, right. So, then how much time would one revolution take? 1 by 50, right, what is that? 1 by 50 is going to be 1 revolution of crankshaft is going to occur in 20 milliseconds, right. Do you agree? Okay. So, typically these valves need to be opened and closed in half a revolution, that means around 10 milliseconds. So, imagine that like in 10 milliseconds like the valve needs to be opened and closed, right, and let us say the speed of the engine increases, it is going to be even tighter, right. So, typically when you start an engine and let us say it idles around like let us say 1000 RPM, okay. So, you are going to have around 1 revolution in 60 milliseconds and you can open and close a valve in 30 milliseconds, still it is a small interval of time, right, but as the engine speed keeps on increasing, you are going to have lesser and lesser time to keep on opening and closing the valve, right. So, that presents a unique challenge like for us, okay, to essentially control these valves. Okay. So, we are going to learn how these valves are controlled, okay, and you can notice that many times the intake valve is larger in size than the exhaust valve. Why do you think that is the case? So, even in this figure like by the way this is a cylinder head of a diesel engine, okay. So, that is why you have a fuel injector, a spot for a fuel injector. In diesel engines you have fuel injector. If you had a petrol engine or a spark ignition engine, we will have a spark plug in that position, right. And we have something called as a heater plug, which is also typically used in a diesel engine, okay. So you can observe even from this photograph that the intake valve seems to be slightly bigger than the exhaust valve, right. Why do you think that is the case? Please note that most of these intake and exhaust processes are pressure driven flows. What do I mean by pressure driven flows? That is a difference in pressure between two regions drives the flow process, okay. During the intake process, you will see that the difference in pressure is going to be smaller than the pressure difference that you will encounter during the exhaust process. Even in basic fluid mechanics, we would have studied about pressure driven flows. Even if you use a simple Bernoulli's equation, right, you will see that if you consider a reservoir and what to say, a restriction, the speed at the restriction will be proportional to the essentially square root of the pressure difference, right, between the 2 points, correct, if you use Bernoulli's equation. So you see that higher the pressure difference, higher will be the speed. So for the same area you will have higher flow rates, correct. So now typically what happens is that the change in pressure, okay, or the pressure difference during the inlet process is typically lower than the pressure difference during the exhaust process, okay. So you see that you pretty much have the same time, let us say around like 10 milliseconds for both the intake and the exhaust process. Let us assume that the crankshaft is rotating at 3000 rpm, then I have 10 milliseconds for the intake process, 10 milliseconds for the exhaust process. So in pretty much the same time I need to take in the same amount of mass of, let us say, air and fuel, and mass is conserved, although the composition of the gases is changed. I need to pump out the same quantity, right, during the exhaust stroke, right, exhaust process. So the mass flow rates are pretty much the same. Then what do I do, right, I increase the area because my pressure difference during the exhaust process is higher than the pressure difference during the intake process. And so what I do is that, like, I would increase the area of the inlet valve to overcome this difference in the pressure difference, okay. So obviously this difference in size would be more pronounced in a naturally aspirated engine, because we will shortly see that we have already seen yesterday, right, in a naturally aspirated engine the intake fluids are taken at near atmospheric pressure, air or air fuel mixture, right. So obviously the pressure difference is going to be smaller in a natural aspirated engine during the intake process, so they will obviously require a bigger valve, right. So that is the main reason, okay. And we will also see that having a bigger valve benefits us by increasing the so called volumetric efficiency, which we will define when we go for engine performance analysis, okay. We will come to that later, but the primary reason is this, because the delta P's or the change in pressure during the intake and the exhaust process are different, okay. So you need different sizes, right, because you want to exhaust this push in and take out the same amount of mass or matter, right, yeah.
So but why exactly for the same time?
Same time because you need to accommodate other strokes, we are going to look at that shortly, right. So because typically we want to complete the intake process in one stroke of the piston and exhaust process also in one stroke of the piston, okay. So you see that the time available is pretty much the same, so you need a larger intake valve, right. So that is the cylinder head, okay.